to the binaries to be loaded onto the machine. So if you ever heard about it, there is this is a place and route problem that is similar to the one for the FPGAs. Okay. What we use it for, or how we use it. We said that everything is asynchronous on this course. Yes, we have three major events. If one packet arrives, so one neuron has fired in the network, has propagated the packet to one particular core. The core there sits and waits until something happens, receives this packet. Oh, I need to do something now. So checks in the memory, puts the spike in memory, triggers a DMA to say, oh, to which are the synaptic weights and the neurons to which I need to propagate this. Updates the synapses in case there are learning rules applied, and place the weights in a bin to say, oh, at this point, this neuron will receive this particular injection of current. And last but not the least, there is a timer event. This timer event is what brings the simulation forward, performing an integration of the mathematical model of the neuron. How many people are sleeping at this point? Well, if you can compare what we pull out of Spinnaker with Brian and Nest, and yes, there are some differences, but not that much. Why do we have this difference? Because in the core, while Nest and Brian use a workstation which is able to perform a floating point operation, Spinnaker doesn't.
I misread that as brain. So the human brain would have a different characteristic.
Well, Brian.
Yeah. Not brain.
So what is this right graph represent?
This is the current injection and the firing rate. And again, current injection, firing rate. Okay. And that's just a time plot, so time, membrane potential there.
So you simulate a leaky integrator.
You can change. You can develop the model you want. We have a leak integrated fire. We have Enzikiewicz. We have probably an adaptive exponential, which is currently under debugging. But since they are programmable, we have also something completely unrelated to neural networks. We have a heat diffusion software. So you start from one point which is very hot, another point which is very cold, and you see how the heat diffuses in this system. It's a finite element analysis. Okay? As I said, there is a synaptic plasticity also available. Here, this is using a pattern immersed in the noise, and you can see it was the network was trained to identify it. But then we have the interesting bits, which are robots, and the robots are always Where is it?
That is very good.
So, this was in Telluride a long time ago, actually. This robot is an omnidirectional robot, and on the top there is a silicon retina. The task is to follow the line on the table. and then I try and avoid that the robot suicides. The retina is actually the silicon retina actually detects the change in light in the phase, in the area, in the visual area, and emits an event, a spike, when the light changes above a certain threshold. So it's not a raster camera as we are used to, but this only detects change in light. In this case, this was connected to a computer, then to the spinnaker board, and back. This was an old board, and back to the robot to control it. This is probably a bit low resolution. Let's see if we can see anything. It's the same robot with the same retina, just a little bit more. This is just wireless. This is the difference, and tries to track the position of the light in the visual field. So, moving the light, the robot follows it. And you can see there on the computer the result of the what's the output of the camera of the silicon retina. But then, if you go to a microcortical circuit, this is, for example, a small microcortical element. The entire simulation only lasts for 1 second. But you can see here the time is about 10 seconds because we are computing this at much higher resolution. So the integration step is not 1 millisecond as always, but it's 0.1 milliseconds. So each millisecond takes 10 time step to be processed. This is why it's slower, and each of these is one of the layers inhibitory, excitatory for the microcortical column. So, the original project included 1 billion neuron on a massively parallel architecture. We are going through it. Now we just finished the 105 machine. We will, before the end of the year or beginning of next year, we plan to complete the final chip, the final machine. But nonetheless, we are already thinking about the next step, which is a 22 nanometer technology chip, 3D. And that has been taken out and we are waiting for the first batch coming back, probably March next year. Not sure, don't know exactly what are the times there. What is the time scale there? Brains represent a significant computational challenge. Why? Because we have a lot of neurons. It's not the complexity of each of them, but it's just the amount of neurons that we carry with us. But since we have all these simple units, are we now getting in range with our technology to try and emulate it? Well, it will be an interesting challenge, even in the next year, to see how much of it the Human Brain Project is able to reproduce. Spinnaker is driven by the brain modeling objective, and has a few characteristics that try to emulate the brain. But the major architectural innovation is actually the multicast propagation. It does self-tuning at many levels, but most important, we have some working hardware. Okay, so this is the group in Manchester. This is a picture taken a few years ago. So, and these are all the people involved who have been contributing on and off with to it. Any question?
Can you have a fully connected, you simulate a neural network which is fully connected?
It's one of the topologies. Yes, you can describe the topology. Then, depending on the size, if it's fully connected, you may need to spread the things a bit more. So there is the design had as a constraint, not as a constraint. The design specification were that there is a 10% connectivity of each neuron towards the other neuron in the machine. So it's not an all-to-all. Perhaps if you do an all-to-all, you may need to spread the computation over a larger number of cores. But in theory, yes, you can do it.
Does it actually matter? I don't understand much of that, but does it really matter what is the physical reality? Because you're doing routing anyways, so you can connect any node to any node.
The problem is that on the software end, when a packet is received, you need to propagate it for each neuron. So you just repeat an operation more times, and that is where the limitation in the computational power comes in. Okay.
So you mentioned that you can do Hodgkin-Huxley models.
Yes.
There's no Hodgkin-Huxley running
No.
currently. But if you did a Hodgkin-Huxley model with, it depends how many compartments you have, right? So if you did a 10-compartment Hodgkin-Huxley model, could you just run one processor? Or?
You can run one Hodgkin-Huxley probably per processor, or perhaps if it's too complex, you may need to spread it over multiple cores. It's not a problem.
I think you mentioned it, and I didn't understand it. It seems to be one of the guiding principles of the Brain project is this bounded asynchrony. And why is it bounded? Is it because of that you have this sort of kind of, there was something in the end of your talk where you said like you have some sort of moment where you try to
it's an event. So you don't know what is the sequence, how the sequence, the events are coming in. You just know that you have a response for each of the events, and that's the maximum that you can tell to the processor. So if you know that there is a packet coming from the network, the only thing that you know you can do is pick up this packet and put it in a queue to be processed. And this is one of the threads, if you want to see it that way. So you don't know when it is going to come, but you know that you will perform this operation. As much as you know that if the timer goes off because at that point 1 millisecond has passed, then you know that you will integrate over 1 millisecond all the neural models, and this thread is different from the one which actually receives a packet from the network. But while you are integrating, it's very likely that you will receive a packet. So there is also a, how do you say, the events may be interleaved somehow. Okay. Yes.
So there's been a lot of advertising and marketing about True North.
Yes.
How will this how does your chip compare to True North?
So
and I use the word compare as
yeah, okay. But there are a lot of things here. So, for example, True North has a fixed neural model. You know that True North will run only, if I remember correctly, Isaac-Illich neurons. And that's it, because it's designed in hardware to do that. It cannot move to a different neural model. Or synaptic models. The synaptic models, you know, that will have always that equation, and you cannot change it. So they have a different approach. But on the other side, I must say that True North is also much lower power than this. So they are different. They have been they've been designed on different principles. Okay.
Yeah.
There is no learning on True North. Here we have learning. It costs in terms of computational power, but you can apply it. True North doesn't, and has a very limited set of synaptic weights. Okay, it's a trade-off.
Yeah.
If you see also other neural network simulators, there are other, each of them represents one point, one dot in the space of the possible trade-offs for the simulators.
So you had one of your 5 things architecture conclusions. One of them was applications.
Yeah.
What is this?
What can you do?
You got not what can you do? What has been done?
What
Yeah.
has been done?
Yeah.
Neural network simulation in terms of a microcortical column or controlling robots. Nango. Have you heard of the neural engineering framework? I guess you have. There is also the neural engineering framework on Spinnaker.
Yeah. So they're doing that to have robot follow the circle.
Yeah, that is one of the ideas.
But
So in
they actually have running.
Yeah, running in real time. So if you take their spawn model, for each second of simulation, it takes 2.5 hours each second.
Right. If they're running Nango on a.
If they run Nango on a single workstation. If they run it on Spinnaker, it's real time.
How big of a Spinnaker are they using? Are they using a?
They are using, it's I think it's a three board system. But if I understand correctly, they are doing they are going now for a 24 rack, 24 boards to go for something bigger. At least we found someone who can fill in all those boards with inter-scene computation.
Okay.
Yes, there are some obviously very well established characteristics of real neurons in the brain, which we don't really understand yet. For example, neurotransmitters. So there are chemical synapses, and the brain uses a lot of neurotransmitters. And biologists still don't really know what they're doing. And there are also glia cells.
Glia cells and astrocytes, and there is neurogenesis, and there is synaptogenesis.
Yeah, so one thing is to simulate a billion or 100 billion of neurons as they connect.
Yes.
But that doesn't actually mean there are obviously some extra things that the brain carries, which is
Yes. And the more we go in the
functional?
future, it's software. It's programmable.
So you could actually.
You can program it. If you spend enough time, you can do it.
Maybe one thing.
If you know what it does.
Yeah.
So if you say an astrocyte does X, then you can implement X, but it doesn't mean an astrocyte does it.
I read all this development of neurobiology or neurobooks, and the interesting thing is that the number of as the number of neurons increase in for example, from worms to let's say jellyfish or starfish to worms and other things, the number of neurotransmitters seem to correlate with the number of neurons. That's an interesting.
It's an interesting
But
one.
when it's
I can tell I don't know much of the wet biology and the experiment, but it is interesting.
Yeah.
But if you have a model, if you know what it does, you can develop something, or you have a theory of what it does, you can test it through something like this.
Yeah, my question was just about this Pine or whatever it was called. And you
Yes,
said,
Pine.
Do you know it? So is this Pine model which you've shown, or this kind
No.
of programming model?
Okay, it's a programming language which describes neural networks in terms of populations and projections. So it comes out exactly as a graph.
And it's
Which-
exactly that medium you were talking about. That's the way you use to program your
Yes,
massively
it
powered
is.
computer.
That's what I was trying to get you to do.
Yeah, no. Sorry. Could recognise that.
So how many mice to the human brain roughly? If a mouse is one cabinet, I mean, how many
Yes.
cabinets are we worth?
Well, 10 cabinets are 1% of the human brain.
Okay.
So if you want to go higher than that, you need 1,000 cabinets probably.
So sort of Amazon-style data center, Googleplex
Yeah.
might just cover it.
But then you go from 90 kilowatts for 10 cabinets up to multiply by 100.
Google have their own power stations. It's not a
Yes,
problem.
exactly. You need the nuclear power station right on your.
But
on
you
the
have
doorstep.
problems with that because you're routing algorithms, isn't that right?
Sorry.
So you couldn't just plug 100 more racks in, right? You're stuck with 10 racks. You have a routing problem once you go beyond that. I'm asking that.
You
tell me.
can. Okay. There is a research point there because you can work around this problem. So if you know that one population only touches a small portion of the
Right.
machine, you can reuse the same idea of the population in a different portion of the machine.
It's the same idea they had in the internet with IP version 4 didn't
Exactly.
work anymore.
Exactly.
No one actually has its address, they just share them.
So I'm not very familiar with this simulation. So in your area, is there any a benchmark index to show the power cost?
There isn't. This is one of the problems that we are trying to face now. So there isn't a standard benchmarking as there is for algorithms or general purpose computation, let's say.
That's what Anders is working on, right?
Yes, there is one portion of the Human Brain Project that is trying to find what is a suitable benchmark for neural networks.
They do have a couple. So they have associative memory,
Yeah.
and it runs on Nest. So just a PC simulator runs on Spinnaker, it runs on Hyphen right now, I think. Oh, and they also have it run on not FPGAs, but graphics processors.
Oh yeah, GPUs. Yeah. There are too many indexes at the moment. There is the number of units, computational units that you need, the memory required, the bandwidth between the memory. There is the power consumed. There are too many that you cannot actually say, oh, this is better than this other. Okay.
Thanks very much.
Thank you.
Thank you for inviting me.